Welcome to my presentation, which is called Afterlife. Originally, this talk was supposed to be called Life After Polysemy. So some of you might know, I actually have been advertising Polysemy library for quite some time. I think it's an awesome library to build maintainable software. It leverages free monads and a little bit of type level programming and allows you to write a really beautiful maintainable code. However, even though my best interest of trying to advertise it, I somehow managed to not convince all the people I was talking to, both at work and social media and whatnot. So I had different opinions about why they would not be interested in using it. So one of it was, well, Polysemy is too slow. And then, okay, I understand that if, for example, you're building some engine which is supposed to be super fast, or I don't know, high frequency trading or whatever, where each millisecond counts, then yes, effect systems might not be the place for you. But if all you do is, I don't know, push JSON from one service to another, where most of the time your code really spends in I/O, the overhead that the effect system will give you to the time you spend is minimal, especially compared to the benefits that you get from effect system. But then I get the argument. Then again, I would still point to a very nice quote that I found on the web, is that Joe Armstrong once said that, make the code work and make it beautiful. And if you really have to make it fast, most of the time it will be fast enough if it's beautiful. So you just should focus on making your code beautiful. As I will just leave it as it is. The other statement I would hear from when talking to colleagues and friends and people in the community was that, well, MTL is very well recognized in Haskell community. We've always done things this way. I will just leave Grace Hooper here again, that we've always done it this way is probably one of the most dangerous phrases in the English language. So the one last thing I heard was that it's more complex. Like, we don't have time to train people. We're just simply too busy. So I will just leave that little image as a counter argument to that. But anyway, things are the way they are. I mean, people are trying to fight it. So here's Alexander Granin with his latest book. You probably might heard about Sandys McGuire, also latest book. So there are people who are trying to push the frontier forward. But sometimes, just sometimes, you will have to stick with the MTL stack. And that's how things are. You will not be able to use effect system in Haskell. My talk is called Afterlife, and it's basically a name of the show by one of my heroes, Ricky Gervais. It's a show about a man who lost his loved one, and he's considering killing himself. So this is me, basically, somewhere around mid-February, when I understood I won't be able to use Polysemy at work, considering killing myself. But the same as in the show Afterlife, spoiler alert, the guy does not kill himself. I also did not kill myself. And luckily, because a few of my colleagues found a nice encodings that makes MTL bearable. And we call it MTL Batteries Included. And this talk is basically about that encoding. So whenever I talk about encodings in Haskell, or as basically any language, whenever I talk about maintainable software, I always have in mind three things. I want the way how I encode effects, how I encode complex problems to be horizontally composable, vertically composable, and testable. So let me introduce those concepts with an example. So imagine that we are writing a application for some company who's selling tickets to events, right? And we want to implement this function where we are basically allowing someone to buy a ticket. And let's imagine that we are on the meeting and somebody from the business explaining to us how this sort of should work, how the thing that we're supposed to right now implement should work. So we are in front of the whiteboard and they are drawing a little application, and they also, so they say like, okay, so when somebody is calling you, what you have to do is basically call payment system and send them like payment information, credit card and whatnot. So that's the first thing that you have to do. And secondly, you have to also call the reservation system. So you have to call it that with some prepared request, and that's pretty much it. So thinking, okay, this is simple. Then some architect, some microservice architect will tell you, oh, the payment system actually works the way you call it through Kafka. So you send this request to payment system via Kafka. And we are, for the reservation system, the way you create a reservation in the reservation system, you have to store a value in the key value store, React key value store. So when I talk about horizontal composability, what I mean by that is that I would like to write my functions in a way where I can talk about separately about payment system, separately to talking about reservation systems. Those are two separate things. In my user story, which I'm supposed to use both, I want to compose them together. I want them to nicely together compose one to each other. So that's the horizontal composability. When I talk about vertical composability, what I mean by that is that when somebody tells me, you know what the payment system really is? It's sending message to a Kafka. Oh, and by the way, the message that you will have to send needs to have a current timestamp when you created that message. So immediately when I hear that, I know Kafka is really hot right now. It won't be probably in 2 years or something, right? There's always something hot. The concept that I want to talk about is basically queue. It might be Kafka, it might be SQS on Amazon, it might be some other streaming or queuing mechanism. When I talk about payment system, I know I have to send message to a queue. I know I have to generate some timestamp. What that queue is, how I treat that queue, that it's Kafka, that I have to deal with Kafka errors, is a completely different thing. So what I want, the way I want to write the software is in a way that when I want to in my user story just say call payment system, and I don't want to be bothered with any details because I don't really care in that abstraction level what that means. When I talk about what payment system is, I want to say, oh, payment system, when somebody wants to pay, we have to send this message to this queue without even telling what the queue is, and we have to generate a timestamp without even talking how we generate it. Then only when I talk about the queue, I want to, oh, by the way, queue, well, we have a few different implementations for it. You might send things to Kafka, or you might send things to SQS. So we slowly, so the problem that we have might be complex, but we have these layers like an onion. We can take one layer at a time and dealing with composability one layer at a time. So this is when I talk about the vertical composability. And lastly, testable. I want to write tests for such a simple user story as, you know, buying a ticket, where I'm just supposed to pay for the ticket and then call the reservation system. I don't want to, for that, I don't want to write a integration test. I want to write a simple unit test where I say I've paid the payment system and I call the reservation system with a proper request, and that's it. Well, it's Kafka. It's going to have like problems, issues, and complex. Shouldn't you write an integration test for it? Yes, I should, but that should be on a different abstraction level. That should be way below where I deal with Kafka, where I implement the queue using Kafka stack. So let me show you how that works. So the way it works is that I have I mean, this is how we can at least try to make it work. So we will create a type class called payment system with a single method pay that takes a request and returns a unit. So request has some UID, a credit card information is over here. Now, in order, like this talk, maybe some of you folks might not be familiar with this. This calls from deriving strategies, because we'll be using different ways to derive type classes for our types. So, but given the time that I have, I really cannot really go into detail. Just for folks who might be interested what that is, the deriving strategies is probably the place in documentation when you want to go. So anyway, we have this payment system. We have a single method pay with which takes a payment request. We also have a reservation system, which has a function reserve. It takes a reservation request. It has like an event ID and seat and whatnot, and also give us a unit. Once we have those two abstractions, so a payment system and reservation system, which are here imported with qualified name P for payment and R for reservation, we can finally write our function, our user story. So here we are saying, if somebody sends us a request and some UID uniquely identifying this request, what we want to do, as you remember from the business meeting that we have with business people, is that we want to call the payment system with a created payment request, and we also want to call the reserve system with created reservation request. And that's pretty much all we want to do. You've seen me using here, this is just using lenses with a little bit of magic. And if you want, I think Alejandro is doing a talk about lenses, but stay with me. Just basically just takes the payment information from that request. That's all the lenses that we're going to see in this talk. Right. So we have that request. And that's well, that's pretty much it. That's the whole function. That's the whole complexity of it, right? Obviously, there's a lot of complexity in the payment system and the reservation system. But as when we talk about just this particular user story selling ticket, that's pretty much all there is. Okay. So now, what it means to pay using a payment system? Well, as I said, we will need to generate a timestamp, and also we'll need to be able to call a queue mechanism. So we create type classes. We create a queue type class. We just have a single method send, which takes a value and returns a unit. And also we have a type class representing time, which gives us the ability to fetch current time. There are a few additional extensions that we need to have. If I have time, I can maybe explain how those works and why they are needed. For now, for people who just seen Haskell 98, those are the extensions that you most likely will always turn on when writing a little bit more complex things in GHC. All right, so we have those two lower level type classes like queue and time. And now how we can implement the payment system using those? Well, this is quite straightforward. We create an instance of this type class payment system. And we are saying, listen, this instance is created for some type M, and we don't really care what that M is at this point. We don't have to know what that M is. We are just saying it has to be a monad. It needs to have an instance of a queuing mechanism where the values will be payment message, and it needs to have ability to fetch current time. If it knows how to do that, then we're fine. And this is the instance for this type. We don't really have to know at this time what the type is. So then we fetch the current time for time. We create our payment message, and then lastly, we send that using our queue function. So far, so good. But oh no, wait, it doesn't compile. Crap. It needs something which is called monolocal binds. And if you Google what monolocal binds are, what this extension is, it's like a super weird explanation on GHC Wiki. But I found this. So if we turn this on, it actually compiles our code, which is great. But like, what the hell we just did? Well, I found those engine scrolls. Here, Simon really explained what it does. And if you're interested, like in a nutshell, if you have a function like that, the G here in a where clause or in a let clause is super polymorphic. So here G is being used where the Y is a char, and here G is being used where the Y is a bool, and it compiles. But if you turn on monolocal binds, suddenly this code does not compile. The G is set to a particular thing. It's either character or Boolean value. So just turning this monolocal binds makes your code a little bit more strict, a little bit less polymorphous, I would say. Nothing really scary other than the wiki explanation of what it is. When I first read the wiki explanation, I was like, what? I don't even understand half of the words. Anyway, we have right now the implementation of queue, which is great. We now want to implement the queue, and this is one more time something trivial. We know we want for the queue to work using Kafka. Great. We have a Kafka send message. So imagine this is some functions from some library. It uses I/O. Obviously, some dummy implementation here, but this is something that you would take from package, right? So it takes a value, it takes a Kafka topic, and it sends it to Kafka. That's pretty much all it's doing. So here we are creating an instance for a queue when we are saying, okay, so it's going to be an instance for Q for some M. We don't really care what that M is. It has to be a monad. It has to have an IO in it eventually, because we are dealing with an IO. And by the way, we need to get access to Kafka topic. So if we could have like a monad reader for Kafka topic, that would be great. And with all those constraints, we can implement that instance. This is great. We still don't know what the M is. We don't care at this point. We are able to implement the instance of a queue. Awesome. We are actually doing a lot of progress here. So here we have finally a implementation of our payment system using all that. One last thing, obviously, that we need to implement is an instance of time, because we have queue. Now we need to have time. This is at this point, this is trivial because we just use a clock, data.time.clock from a type library, which just gives us a current time in IO. We lift that and we're good. So instance is trivial. Once we have that, we have basically everything that was needed for the payment system, nicely layered. You know, we strap the complexity one of the other after the other. We have to do the same thing for the reservation system, right? So as you remember, reservation system was a type class that takes a reservation request and returns a unit. Now we need to instantiate it. I don't know if you remember, our architects told us that it's when somebody calls a reservation system, what we should do is just put an entry in React key value store. Great, but as you remember, I said we don't really have to talk about React key value store. We can talk about key value store, and later on discuss whether this should be React or maybe Mongo or maybe some other key value store that you have, maybe something even in your memory if you want. Okay, so we just need to have a lower level type class called key value store, which takes a key value and returns a unit. Now, once we have that type class, we can implement the instance for our reservation system using it. So here we're creating an instance for reservation system for some M, right? But we don't still, one more time, we don't know what the M is. We only know that it has to be constrained with a monad and key value stored. And having that, we can use the put function and everything works just great. Okay, one missing piece is implementing the key value store. As I said, our architect told us we need to store it in React. So one more time, we have here like a library, probably somewhere for package. So it takes a React bucket, key and a value, and returns IO. So we can use this function. We call it React store. Interestingly, we store the key and a value for a bucket. As you remember, with a queue, we also read what the Kafka topic would be from monad reader. We are not doing it here. We're storing everything in a bucket called everything, and there's a reason for that. It looks weird why we didn't use monad reader here. Well, we'll get to that in a second. But for now, let's just say we're just going to store everything in a bucket called everything. Great. So let's recap. We have this sell ticket functionality user story that uses payment system and reservation system. Payment system is implemented using queue and time. Queue is implemented using some Kafka library. Time is being implemented using time library. And we also have a reservation system, which is implemented using key value store type class, which itself has an implementation using React. We can try to use it in production. So the way we're going to do this, oh, by the way, like I'm creating here in where clauses some requests, credit card, and seed. I will just hide that because there are only like limited number of lines I can have in a slide. But you can imagine those things are just being here created some constant values, credit card, seed, and the request itself. So in the main function, and you can think of it as this can be like an entry point. It can be your HTTP endpoint or whatever. Here we just have a simple main function. We generate new UID. We call our sell ticket function with that UID and the request. And once that is being called, we hope this will give us something that holds all those constraints in type classes and instances. So we think it potentially would be good if that was a ReaderT of Kafka topic of IO. If that's the case, then we can just call run ReaderT with Kafka topic, which gives us an IO and everything should compile. And actually it does. So it works. I I was supposed to put a slide here with this running, but yeah, I forgot. Anyway, this compiles and it works and it runs. So all the instances were constrained, but all the constraints are being met. The major constraint here was that because the queue was using Kafka implement instance with a Kafka in it that would constrain itself with a ReaderT on Kafka topic, we have to call that run ReaderT in order to unwrap the IO that was hide in it. Great, but you remember, as I said, like this is bizarre, right? Like, why are we using React bucket everything? Why can't we, like, the same way as we have had in the queue? Why can't we just constrain here, say monad reader, React bucket, and be done with it? Well, we can actually do that, right? Like, let's do it. So here, instead of hard coding the bucket, we will just say, there's this type M needs to have ability to grab the React bucket, and we call the ask function from monad reader that gives us a bucket, and everything works as expected. The only problem is, so now we hope that like this should work, right? So the type that we are hoping to get is a type that will have a ReaderT of Kafka topic, of ReaderT of React bucket of IO. We hope this will work, but hey, it doesn't, because it's saying that Kafka topic is not React bucket. And I'm like, why would it be? I mean, it's recognizing here, it's recognizing here what I wanted it to be. So this is great, but why on earth it's not working? And the problem lies with functional dependencies. So functional dependencies, really quickly, Jesus Christ, time flies. So I will probably take more than 45 minutes, probably like an hour, if Shannon will not kill me. So
fine. If you're kind of happy going on, then we've got a 45-minute break after you, so we can always just run over a little bit.
A little bit. All right. So I'll try to go as quick as I can. So okay, so we have a type class. So here's an example what functional dependencies are. So here you have a type class foo with A and B in it, and a function from A to B. Right. So you can create an instance for foo for string and int, and for int and int, and everything will just work great. This will compile, and you can actually use it. If you call foo with a string, obviously this instance will kick in, and you will get a value 10. Great. This compiles. But now if I call foo string, this code freaks out, and it's telling me it's not able to realize which instance it should use. And I'm saying, like, what? It's obvious, right? Like, you call this foo with string, so this gives you an int, and then you provide that int to a foo. This should be quite trivial. No, because Haskell is completely aware that you can do the next thing, which would be provide an instance from string to string. So now when you call foo string, which instance should it use? The one that returns an int or the one that returns a string? So it doesn't know what the type of this should be. Obviously, you can make it compile. You can tell it, well, it's supposed to use this instance. It's supposed to like return an integer, and then it will be happy. But there's another thing you can do. You can use functional dependencies. So what you can say is that you have foo parameterized by A and B, but A uniquely identifies B. What that means is it's telling you that if you will have an instance of foo of some type A, let's for example string, and then int. There's no way there will be other instance where A will be a string. So this other instance here should not compile, and it actually does not compile, as we can see over here. So in order for this to compile one more time, we need to create that instance, and now we can create of this monstrosity here, and everything works just great. So now the question is, why monad reader? Well, because monad reader is using those functional dependencies, and the question would be why that is. So here we have a simple version of monad reader with a ask mr and nothing really else in it, some instances and some usage of it. So here I'm just saying like, hey, I have a my monad reader of int, right? And I'm asking for that int, give me that int, and I want to show it to all the people in the world. And the compiler is telling me, no, you can't, because I don't know which instance to use. And I'm saying like, how on earth you don't know which instance to use? Obviously this should be I, right? So this I should be an int. And if I tell it this should be an int, he's completely happy. But it couldn't derive that information before because we didn't have any functional dependencies between M and R. If we provide those dependencies, so if we say that M uniquely identifies R, then all is good. We can only have that one single instance here. And when we call like my monad reader int, it will know exactly which instance we want. This is great. However, the problem is, if we try to do something like following, so we have my monad reader with functional dependencies, and I have function G. Right now, function G it works on some M, right? And that M is constrained on monad reader for both integer and string. And if I write a code that looks like this, I want to say ask I, give me an integer, ask as, give me a string. Those are the things I want to return, integer and string. This code compiles, actually. But when we try to use it, then it freaks out. And it's telling me, oh, string is not an int. And I'm like, yeah, I know that. So because of functional dependencies, this is not doable. Interestingly enough, we could actually fix that in this implementation. What we could do, we could provide one more instance, this instance over here. So this instance is using a overlappable. This is another extension that you have to turn on in your Haskell program. But what it's saying is, if you are trying to make a resolution of an instance for a particular type, and both of those instances apply, don't use this overlappable instance. However, if only one applies and it's overlappable, you can use it. So here I'm saying, oh, if I have a ReaderT of some other R, some different R, but I'm actually trying to get a monad reader for a different R, but by the way, that internal M has an instance of it, use that instance. So just lift it and ask and be done with it. If we have that, then, and because of the time limit, maybe in Q&A session, if people are interested, I can dive deeper why suddenly this function works and this usage actually works. So maybe in Q&A, if people will be interested. But, and by the way, there was a PR that I tried to provide that into MTL implementation, but it was rejected for the reason was it's betraying MTL. And I was trying to ask, why is it betraying? But I didn't get an answer. But anyway, this is the way, this is the life we are in, right? If we have a code that looks like this will not compile. It's basically where we left our little main function before, right? We were hoping to have two monad readers with different R's, but that is unfortunately not doable. Great, but there is a way we can sort of like handle this. There's a library in a package called Data.Has. It comes with a simple type class called Has. So Has.at gives you more functions, but this is the one we're going to use. So it gives you a function getter. So if you have an instance of A and T, it gives you a function that from T will give you an A, and some instances. And those are trivial, right? Because if I have a tuple of A and B, right, this is the T, I can always give back a B, or I can give back an A. And if I have a tuple of A, B, C, I can give you a C or B or A, and so on and so forth. So there's this tremendous amount of instances implemented for different tuples, and we can leverage that. So instead of saying when we have our key value type class and an instance for it that was previously using monad reader, right now, instead of saying monad reader React bucket, we can say, you know what, monad reader of some R, we don't know what it is, but it needs to have a React bucket in it. It can be just monad reader or React bucket, but maybe a tuple where React bucket is inside that tuple. Okay, and then we have to call, instead of calling ask here, we need to call asks and provide that getter to actually fetch the bucket. So we do the same thing for the queue. Instead of saying monad reader of Kafka topic, we will say monad reader of some R. And by the way, that R needs to have Kafka topic in it. And one more time, asks getter, which will give us a topic. And now the only thing when we run our function in May, instead of, we still only can work with a single reader, but this time it's going to be a ReaderT of a tuple of both Kafka topic and React, which they have the Has instances for Kafka topic and React, and everything compiles and everything works. With the amount of time that I have, let's try to write some tests. Okay. The tests I want to write right now is just for my user story. Nothing else. I'm not writing tests for key value store integration tests or whatever. I'm not talking about React. For now, I just want to say what the business people told me. They told me that when somebody tries to buy a ticket, the first thing I should do is I should call payment system with a payment request, which will have a UUID and a credit card that I got from request. So this is the test I would like to write. I would like to generate some UUID. I would like to call my function, but now my function needs to work with some effects, right? I don't care about the reservation system. So the instance for the reservation system could be just, no op, do nothing. I don't care. Like somebody calls you reserve for this test, I don't care. For this test, what I care is to know if the payment system was called, and if it was, how many times, and what was the value that it was called with. So I could write an instance for the payment system for some M, where that M needs to have an ability of a writer. So it has a monad writer. We can store some values in it, right? Like a WriterT would be an example, WriterT of like IO, for example. And that's exactly what we're doing. So we are saying when somebody calls pay request, tell is function for monad writer, store this request in a list. And a list, because list is a monoid, so we can compose results later on. So then when I call this function, this hopefully will be like a WriterT of IO, then I execute the writer, and I should get a result, which should be a list with a single payment request. Life should be good. This test should actually pass. Let's see if it does. No, it freaking does not compile. Jesus Christ. Okay, it's been like 40 minutes and we still don't have a compiling code. Well, we have something that's working, but we cannot really test it. This is not good. Okay, why can't we compile it? Like, why is it complaining, talking about duplicated instances? I mean, yes, I know I have a production instance for payment system and a test instance for payment system, but those are completely different instances. They are constrained with different things. The production one is using queue and time, and the one that I use in test is using writer. Shouldn't GHC recognize this? Well, unfortunately, when GHC is doing instance resolution, it is only looking at the things on the right-hand side. It's completely ignoring the head. So the head eventually will be used when it's going to try to compile the functions in it. But when it tries to make an instance resolution for your type, you have some type and it tries to pick up an instance, it only takes into consideration things that are on the right-hand side from the fat arrow. So we've created basically two instances for payment system for any M. This creates an instance for any M, and we have two instances like that, and GHC cannot differentiate between which one to use, and that's why it's complaining. So the question is that it? Is that the end of the presentation? Should we just use Polysemy? And well, no, there is something we can do about it. Okay, so we're going to use something which is called default signatures. So default signatures allows us to write a default implementation in a type class. What I mean is, remember how we have a queue, which was just a type class, and there was some instance written for it with some constraints like MonadReader and has and show and monad.io and whatnot. With that extension, we could write that implementation within the type class itself. So we can say default implementation of this function is following, but you can only use that default implementation if your type M going to have those constraints. Okay, we can do the same thing for, and by the way, if you have a default implementation, when you create an instance and your type mismatching all those constraints, that implementation of a function is going to be used. So you don't have to implement it your own, it's already done for you. So we will do the same trick for all the type classes that we have. So instead of having a type class and an instance with some constraints, we're going to have a type class with default implementation with some constraints. So that goes for key value stored, that goes for time, that goes for payment system as well. So all of them are getting default implementations. The same goes for reservation system. Life is good. Now, in the main function, these functions stay almost the same, but we just created here this new type app, which underneath holds the ReaderT, something that we had before. Previously, we were using in the main ReaderT of a tuple Kafka topic in React bucket. But now we've wrapped that within the app, and the app has a monad.io and functor, and all that is being derived with a new type deriving. We all derived that from the instances of ReaderT. So the monad reader, the applicative, all of that was derived for this type app. And now we can create a bunch of instances, and this is valid code. This will compile. It's not like I forgot to implement it. It's using the default implementations, because the default implementations were all provided for those type classes here with some constraints, but this app holds all those constraints. So this will luckily compile. So then we call our main function. We simply just call it with, first of all, it will call, and the type is going to be an app. Here, this is going to be an app of ReaderT of IO, which we then call an app, which will give us a ReaderT of IO, which we then run and everything works. So now what's the difference? The difference is that we no longer have a instance like we had an instance for all the possible M's. Now here we just created type classes with default implementation, but we didn't create instances just yet, or especially we didn't create instances for any M. In the main function, we create a very specific instance just for the app, for nothing else, not for generic M, just for that particular app, which allows us finally in our test to do somewhat similar trick, where we create a new type test, which will have a WriterT in it. So we almost do the same thing as we did in main, and we derive all the needed things. And we create two instances. Well, for the reservation system, for test-T, we still don't care what that is, because we just call pure. We don't really care about the reservation system at this point, but only we care that if you call payment system, you should store that information in the WriterT. And we can call tell here because we derived monad writer from the WriterT from our test-T. So finally, when we call our test cell ticket, this will be a test T of WriterT of IO. We call untest, which will give us the WriterT of IO, which we then execute, which we have in IO, and the result we can check if that's the one that we were hoping to get. And yeah, and then the test pass. This is great. Now, do I have 15 minutes? Something like that?
You've got, yeah, I mean, you've got till about 35 past, but if you need to run over like 10 minutes, then that's fine.
35 past, so I have like till 20 minutes?
Oh, no, 30, no, like just under 10 minutes.
Oh, so I have 15 minutes. Well, that's not great. But yeah, let's try to do this. Okay, so I'm actually not that far away, so we might get it. Okay, we've written the first test. So what do we have right now? If we have a working implementation, and we just wrote a unit test for it. So things are going good in a good direction. Now, the problem is if I now want to write a similar test in which I will call the cell ticket function, but now I want to reason whether the reservation system was called, well, this is getting more tricky because I have this test T and I have both instances for payment system for test T and reservation system. I mean, you know, I could potentially have here instead of tuple of payment requests, could be like a tuple of either payment request or reservation request, but this, you can probably see this will not scale. It would be nice if I could have a separate type that would represent the effect of a payment functionality, separate type that would represent the reservation system functionality. And this is exactly what we're going to do right now. So before we write this test, let's try to maybe refactor what we have right now. So this is what we had right now. We have a test T instance for it for payment system and no up instance for reservation system. What we can do is, well, we can first of all maybe rename it a bit. So here, something we had before was a test T. Now we just call it writer payment. This should be called payment system, not payment request, but just a name, doesn't matter. So it's almost the same thing. You remember how test T was holding a writer T? Now we have we just renamed that really, and nothing really else about it. It still holds the writer T of payment requests. So this stays the same. Well, the instance for it stays exactly the same, but the instance for the reservation system before we just say no up, we already make like a decision for this type. And here we are saying we don't know but we hope someone else will know. So what we're saying here, we're providing an instance for reservation system for our writer payment here for this particular type, but we hope that the M that it holds inside it knows how to do the reservation system. You see the constraint here, right? So what do we do? Maybe I'll just show you the less verbose version of it. So we call the reserve request function, which gives us an M, which then we can lift to a WriterT of M, which then we can lift to the writer payment request, to that little thing. So this instant has no idea how to do the reservation for this type, but it hopes somewhere along the stacks, along the way, there's someone that knows how to do it. So we can just inline it, and then lastly we can provide like a little helper function which would be called run writer payment request, which take this type as an argument of M type MA and give us back the M and the tuple of A and the accumulated list of requests that it gathered when the pay function was being called. So the implementation is straightforward. We unwrap it, the writer, and then call WriterT from the WriterT from the MTL library. Great. So this is done just for the payment system. We have to do the same thing for the reservation system. So the way it's basically the same thing. So we're saying we're going to have a type no-op reservation system. We're going to create an instance for it for the reservation system. So for no-op reservation system M, we just say, oh, we don't know, we don't care. What about payment system? When again, no-op reservation system does not know how to deal with payments, but within the stack, somewhere along the way, it has a type, it has that some M that will know how to do the payment. So we one more time call the pay request, which gives us an M, and we wrap that M over the no-op reservation system. So this instance, one more time, does not know how to do the payment, but it has a fellow type along the stack that knows how to do it, and it just calls it with that type and then wraps it up. Okay. Once we have that, we can call our test and we just say, okay, sell ticket with, so this type, it's going to be that write payment request, which has a WriterT, which has an IO, and that's it. So run writer payment request gives us a tuple of unit and payment requests. No-op just does nothing really, give us that back, and we return the second element from that tuple. So we don't care, it's a unit. We only care about accumulated effects. And the test compiles and the test works. And it has a nice feature that we could choose which effects we're going to use for each of the type class. We use the writer for payments, and we use no-ops for reservation system. So, and we can swap, the order doesn't really matter. We can use one or the other. So now when we want to write a second test, it's basically, we have to do the same thing for, I will just have to skip it. We have to do the same thing for reservation system. So it stored the reservation request, and we have to do the same thing for payment system. So it ignores sometimes the payment request. We don't really care about the pay function being called. And now we can write a second function and we tell, if you call this function, I don't care about payment system. I only care that you remember which reservation requests were being called. Give me back that value and I will evaluate whether this is what I was hoping for it to be. This obviously is so this works, this compiles, and the tests are passing. It has an issue that we have to create all those instances. For now, there's only 2, but for each type class, we have to create an instance for each type class and for each effects that we defined in the system. So imagine that now we have to do this for key value store and for queue and whatnot. This will quickly become like super complex. So we can leverage MonadTrans and overlappable. So MonadTrans is really just a it's just an abstraction of different monad transformers. So when you see T here, think for example reader and ReaderT of M and M is M. So for example, so if we have an instance of MonadTrans for ReaderT, it means if I have, for example, IO of A, lift will give me a ReaderT of IO of A. That's pretty much what it is. And now we can use that little trick with overlappable. So one more time, we can say, oh, if somebody is calling payment system and needs to have an instance of a payment system for some TM, so for example, for a reader, but the payment system exists for that M, something along the stack, along the way the stack. Oh, well, here you go. This is the implementation for it. And it's overlappable. So it means if the type that we are looking for has a different implementation somewhere in our code, this thing will be rejected. This instance only gonna be chosen if nothing else, if there is no other instance for this particular type. One last thing. I really don't like this thingy. I don't like that because we have right now, I have 5 minutes, great. We have now a test that we can write easily and decompose, and we could write the same functionality for Q, for example, and then we could write integration tests for key value S implementation. But this up here, the main function, I still don't like it because the problem is if I look at it, I don't know how this is being used really. Cell ticket, somebody calls cell ticket. Okay, like what effects it used underneath. I see there's Kafka topic, I see React, but I absolutely no idea how payment system works. For example, I would have to go to the instance of payment system, look at the default implementation. It's really bogus and it's hard, and we hold the context in one particular tuple. It's not great. The question is, could we use the trick that we've seen before, that we used for tests? Could we use that for production? And as it turns out, yes, we could. So for each of the types previously implemented with default functions, right, like over here, we could just use the same trick that we used for tests. So instead of having, for example, time, which default implementation that was constrained on monad and monad.io, we could create a type class, just a type class, the effect, which we would call like IO time, with we would just wrap some aim in it, instance for it, which would be constrained by monad and monad.io, overlappable instance, and that would be it. And probably, and we have the call function run IO time t here, and then we would just do the same thing for. I have to really be really quickly. So for folks who are interested, I encourage you to maybe join me in a Q&A session because I really have to jump for the slides. But we can do the same. Like if you're watching this on YouTube, just slow it down right now or just pause it for a minute. We can do the same thing for Q right now. So we could just say, oh, there's an effect Kafka Q. We know how to run it. If you give me Kafka top, so the effect holds the ReaderT of Kafka. I know how to run it. So I know how to go from Kafka QT to MA if you give me a topic. So I will just unwrap the ReaderT and then call it with that topic and be done with it. That's an overlappable instance as well. If you have, things stacked one on top of the other, and then the instance is created for that Kafka QT, really taking the topic and everything as it was before. So we can do all that for our previous, so for key value store. We can do this for payment system. We can do this for reservation system as well. It is becoming a little bit of over boilerplate. I'm completely aware of that. But the nice thing about it is once we do all that exercise and once we start writing type classes using that encoding, the main function becomes this. And this is brilliant because now I call cell ticket, and cell ticket has this number of effects it has to deal with. But I can call run queue payment system. And as you maybe remember, the queue payment system was saying, oh, I know how to run as long as there's going to be somewhere along the way the queue and the time. Reservation system knows how to do its stuff as long as there is a key value store implementation. And those are saying, yeah, we know how to run, but as a queue, I know how to run for Kafka, and I can run if you give me Kafka topic. The same goes for React bucket, and lastly, runtime IO. The nice thing is that if somebody comes along the way and tells you, oh, shit, we're supposed to be sending that not over Kafka, but through SQS on AWS, you're like, fine, because I can write instance of a queue that will use SQS, and I will just simply replace this single line of usage over here. My unit tests will stay the same. For the payment system, at least they don't know what the queue mechanism is being used. All they really care is that there is some queue mechanism that we have implemented. And by the way, the Kafka implementation will have integration tests, which you will know they work correctly with any particular Kafka that you use on production, but you have to test it only once. and never bother with any Kafka issues ever again, especially when you're testing your business logic. I have 1 minute, which is great because this is basically the last 3 slides. So specs stay the same because they run on their own stack. They have their own little no-ops and WriterTs and whatnot. They have their own stack on which they run our function. And that's all, folks. I just really want to say thanks to my colleague at work, Moses, who pretty much introduced me to this stack. And he sort of was pushing us towards using it. We were using some other MTL encodings before. If you are not following Moses, I think he made a mistake. He should be just called here Hackerman. He's missing an H because he is really a true hacker. And if you are into Haskell and you're interested in learning new things, I definitely encourage you to click this button. My name is Paweł Szulc. You can find me as EncodePanda on Twitter. If you enjoyed it, let me know. And that's with 5 minutes of video, I think I'm done. And thank you very much.